How are you all doing today?
Good.
Good afternoon.
So at present, I believe only 6 students have taken exam 1, or excuse me, exam 2. So the overwhelming majority of you, it appears, will be taking it tomorrow, which is perfectly fine. At present, I'm just making sure I'm not telling tales out of school here. At present, it looks like all but one student that has taken the test to this point has passed it. So perhaps I made it too easy. Those students all took it without a equation sheet because for whatever reason Moodle was being difficult and didn't send out the message that an equation sheet was allowed until 14 hours later for whatever reason. So I'm working with those few students who didn't take it to find some sort of resolution. But yeah, so tomorrow, immediately after class, for those of you that have not taken your exam, you are expected to take the test, and it's looking like I would anticipate a class average of somewhere in the low 70s, based entirely on the students that have taken the exam to this point. All right, so what I would like to talk about today, and I'm actually a little bit undecided as to what to talk about. I know that I want to talk about complex numbers because that's going to be a huge part of our upcoming circuit analysis. But I'm undecided as to whether or not I want to also talk about sinusoidal signals today, or if I want to put that off until tomorrow. Typically speaking, a full class period would be dedicated to the review of complex numbers, but I feel that since there's only 9 people on Zoom and me, we might finish that review up significantly early, which wouldn't be the worst thing in the world for me and probably wouldn't be the worst thing in the world for you guys. So I'll kind of make that judgment call with regards to sinusoids once we knock out this complex number stuff. That sounds okay to you all. My hesitation there is because the review of the sinusoids is a bit lengthy, and then to get into the application of looking at sinusoidal waveforms, that together usually takes 2 hours, potentially a little bit more. So if I could get rid of some of that by taking care of it today, that might be a reasonable idea, but we'll see. Maybe I'll just very briefly talk about sinusoids and then we'll get into application tomorrow. All right, anyway, just talking off the top of my head here. So let's start with complex numbers. How many, if any of you, are familiar with complex numbers? Nobody is saying much of anything, so I will assume that none of you have the foggiest clue what a complex number is. So a complex number is a number which contains both a real and imaginary portion. So as an example, I might have a complex number, which I call A, all right? And I identify complex numbers by putting a bar over the variable that I'm using to describe it, okay? Textbooks typically do it by using boldface type, but I can't write in boldface type, so I put a bar over the top. So let's say generically that we have a complex number A who will have a real part, alpha, plus J beta, where beta is the imaginary part of our complex number A. J is the imaginary operator, where J is equal to the square root of -1. So many of you are probably familiar with the use of the imaginary operator I to represent the square root of -1. However, in electrical engineering, we use I so much to represent current that it would be overwhelmingly confusing to use I as a mathematical operator as well. So we use J instead. Okay, so if I were to plot the imaginary number A on the complex plane, where the vertical axis is where imaginary numbers go, and the horizontal axis is where real numbers go, my complex number A might look something like this. Where the projection of A onto the real axis is alpha, and the projection of A onto the imaginary axis is beta. Is anybody confused yet? Or as what I've talked about briefly to this point, is anything not making sense?
It seems straightforward. Your explanation was good, in my
Okay.
opinion.
All right, so we can think of these let me see what's going on in the chat here. All good so far. Great. Okay. So it's good. We have a good fundamental basis of what's going on here. Okay. So our complex number is really kind of just like a two-dimensional vector. It has a part in the X direction, which is the real part, and a part in the Y direction, which is the imaginary part. Nothing particularly wild or crazy there. Continuing that two-dimensional vector analogy, we could see that the complex number A makes an angle with the real axis. I'm going to call this angle theta A. And our complex number A has a particular length. Which I'm going to call A with no hat over it. So A without a line over it represents the magnitude or the length of the complex number A. And we can use simple trig identities to represent that magnitude as a function of its parts, right? So just using the simple Pythagorean theorem, the length of complex number A, or the magnitude of complex number A, is simply the square root of alpha squared plus beta squared, or alternatively, it is the square root of the real part of complex number A squared plus the imaginary part of complex number A squared. And that's how we can get the magnitude of any complex number. Square root of the real part squared plus the imaginary part squared. Our angle, theta A, I'm going to change the color on that real quick, just for the sake of argument. Is given by the trig identity, the inverse tangent of beta divided by alpha, or more generally, the inverse tangent of the imaginary part of complex number A divided by the real part of complex number A. Okay. Now we can take those two quantities, the magnitude and the phase angle, and the angle, and construct an alternative relationship for our complex number. So on one side, I have A is equal to alpha plus J beta. And this is fundamentally equal to A is equal to A e to the J beta A, which is called the exponential form of the complex number, which we don't actually use a whole heck of a lot. Or A with an angle of theta A, okay? So this guy right here, again, is called the exponential form. Not used a whole heck of a lot except for today, because some of the math that we're going to do will make more sense by looking at the exponential form. And this guy right here is what's called the polar form. The polar form of a complex number is what is most commonly used by electrical engineers. The representation that we have over here is what's called the rectangular. Okay. And it's the second most commonly used representation. So we can represent the same complex number in two different ways. And it's effectively the same as what you learned about expressing a number in Cartesian coordinates and a number in polar coordinates back in your pre-calculus class. It's the exact same thing. We're just, in rectangular coordinates, we're looking at how much of the number is in the x direction and how much of the number is in the y direction. And in exponential and polar form, we're looking at how long the vector is and what the azimuthal angle is. So this is all familiar. It's just got a slightly new application here. So what I have written up here, and I'm just going to copy it and paste it and put it underneath down here, is how we transform our rectangular complex number into a polar complex number or an exponential complex number. So it might be useful to now talk about how to go back in the other direction, right? So alpha, which is by definition the real part of complex number A, we can hopefully easily see, just using simple trig identities, is going to be A, our magnitude, times the cosine of theta A. And similarly, beta, which is the imaginary portion of complex number A, is simply A, the magnitude, times the sine of theta A. So I'd like to pause here again and ask if anything is confusing or needs further explanation.
This is just pretty simple trig stuff, so pretty good, pretty easy.
Okay, great. So that's my intent, is that you guys think that this is pretty simple trig stuff that you've seen before, because it absolutely is. Okay. So we have these three different representations, and we can use them interchangeably. But when we want to do math using complex numbers, we have to kind of pay attention to some rules. And so I want to preface this by saying I am going over these rules purely to help you guys understand some of the derivations that I am going to be doing later on in the course, okay? After I finish this explanation up, I fully intend and expect for you guys to do 99% of the complex math that we will cover in this class using your calculators. Okay, I highly encourage that. All right, your calculator literally does not care whether you input the complex numbers in polar form or rectangular form whatsoever. Okay, so effectively the next 10 minutes or so is just me being smart and fancy for the sake of saving myself 30 minutes of explanation later on. I fully recognize and understand that most of what I'm about to do, it will probably make sense to you, but in practice will be largely unnecessary, okay? So let's talk about addition. Okay. Let's say that I have a complex number A that is lowercase a plus jb. Moving away from Greek letters because I'm going to run out of them too easily. And a complex number uppercase B that is lowercase c plus jd. If I want to perform the mathematical operation that is A plus B, all I do simply have A plus JB plus C plus JD will look like A plus C plus J, B plus D. This is exactly how you added vectors together in your pre-calculus class and your physics classes, okay? So we're just adding the real parts together to get the real part of the overall complex number, the answer, and then we're adding the imaginary parts together. So it's literally adding the vectors in the x direction plus adding the vectors in the y direction, just like you added vectors previously. Nothing remotely difficult there. Addition is easily carried out using rectangular form complex numbers. Polar form complex numbers is actually much more difficult. So if you are ever going to do complex number addition by hand, I would suggest that you convert everything to a rectangular form complex number. Subtraction is effectively just addition. So if we have those same complex numbers, A is equal to A plus JB, and B is equal to C plus JD, then the mathematical operation of A minus C, excuse me, A minus B, don't know where C came from, is going to be A plus JB minus C plus JD, which is going to look like A minus C plus J B minus D. Okay, so it follows the exact same rules of addition. We are just effectively distributing that negative sign into the second complex number there. Okay, so since subtraction is effectively addition, it too really needs to be carried out in rectangular form if we are going to do any of this math by hand. Any questions before I move on to multiplication and division? All righty. So multiplication is where things can start to get a little difficult. All right. So if I have A is equal to A plus JB, and I'm going to go ahead and set myself up A e to the J theta A. So these are just two different representations of the exact same complex number. And complex number B is simply C plus JD, or B e to the J theta B. When I multiply A times B, and I want to be clear here, I'm not going to put a dot between them to indicate multiplication, because I do not want you to get confused with the dot product for those of you that have had vector calculus. Similarly, I am not going to put an X or a cross between them because I don't want you to get confused with the cross product. This is simple multiplication. So I'm simply multiplying A plus JB times C plus JD. So I'm literally just going to do 8th grade algebra, FOIL this guy out, right? So I'm going to see that I have A multiplied by C, and then I'm going to multiply A times JD. So that's going to look like JAD. Then I'm going to have JB multiplied by C. So that's JBC. And then I am going to have JB times JD, which is going to look like plus J squared BD. So this J squared right here represents the square root of -1 squared, right? Which is simply -1. Actually, let me. So I could group my real and imaginary terms together and see that this is going to give me AC minus BD plus J AD plus BC. Is anyone confused by these results? Or does anything not make sense with regards to these results? All right, so that multiplication operation in rectangular form isn't particularly difficult per se, but it is a little bit more involved than our previous mathematical operations of addition and subtraction. What I would like to do now is show you what happens when we multiply complex number A times complex number B when we use the exponential form. So we would have A e to the j theta A multiplied by B e to the j theta B. This is simply going to be the magnitude A times the magnitude B to the e to the j theta A plus theta B power. So when we multiply rectangular form complex numbers, the math is a little tedious. When we multiply polar form complex numbers, the math is pretty trivial. We multiply their magnitudes and add their angles, and we get the result pretty dang easily, okay? So you can absolutely do multiplication in either form, but I firmly believe that multiplying complex numbers is much more easy to accomplish using the polar form. Division is where things are going to kind of go off the rails here. So let's say that I have a complex number A plus JB, which will be equal to A e to the minus j theta A. And complex number B is equal to C plus JD, or B e to the j theta B. So if I want to do A divided by B, this is going to look like A plus JB over C plus JD. So I have a rectangular form complex number in the numerator and a rectangular form complex number in the denominator. And what I would like to do is what I've been able to do with all of my previous examples and split that result into a real part and an imaginary part. And in order to carry that out, I'm going to need to use what is known as the complex conjugate operation, okay? So I'd like for us to revisit our triangle that we developed earlier. Where our vertical axis is the imaginary part and our horizontal axis is the real part. And just for the sake of argument, here's my complex number A, whose projection is lowercase a onto the real axis, and whose projection is B onto the imaginary axis. The complex conjugate operation, really all it means is that I change the sign on the imaginary portion of the complex number. So if I had A minus JB, the projection onto the real axis is still A, but now the projection onto the imaginary axis is negative B. And I denote this by putting a star next to my complex number. So this is the called A conjugate, where A conjugate is simply A minus JB, or, so if we know that this guy forms a particular angle with the real axis and has a length of A, when we do the conjugate operation in rectangular form, we still have a vector length of A, but now we've formed an angle that is negative theta A. So any questions regarding the conjugate operation before I apply it? In its most simplest form, conjugating a complex number is simply changing the sign on either the imaginary part if you're in rectangular form, or changing the sign on the angle if you're in polar form. So what I'm going to do, coming back up here to revisit division, is I'm going to multiply this guy by B conjugate over B conjugate. So that would be C minus JD over C minus JD. And in carrying out that operation, I'm just simply going to FOIL things out exactly like I did earlier. So in my numerator, I'm going to have A times C minus JA times D plus JB times C. And now I'm going to have minus J squared BD, all divided by C times C, so that's C squared. And then C times negative JD is going to give me minus JCD. When I multiply JD times C, I get plus JCD. And finally, I'm going to have minus J squared D squared. Recognizing that J squared is simply -1, this is going to leave me with AC plus BD, because if J squared is -1, negative J squared is +1, plus J BC minus AD, all divided by C squared plus D squared. And I could break it up as AC plus BD divided by C squared plus D squared plus J BC minus AD over C squared, plus D squared. Where now things are broken up into an easily recognizable real part and imaginary part, okay? So division using rectangular form complex numbers is significantly more difficult than any of the prior operations that we have done. If instead we do the operation using polar form complex numbers or exponential form complex numbers, we would have A e to the j theta A divided by B e to the j theta B, which is just going to be A divided by B e to the j theta A minus theta B. So I would strongly argue here that carrying out division using complex numbers should be done in polar form, because instead of having to go through that huge big rigmarole of conjugating the denominator and all that kind of stuff, you simply divide the magnitudes and subtract the angles. All right, so any questions to this point? All right, so what I would like for us to spend the next few to several minutes on is doing some simple, my hope here is simple, mathematical operations. And the point here is really to familiarize ourselves with the functionality of our calculators. And this is going to be honestly a little difficult to do because you can't see my calculator and I can't see yours. So what I'm going to try to do is to talk you through things. I have my TI 36X calculator next to me, as well as my Casio FX 115 ES calculator, which are the two calculators that are in use by the overwhelming majority of students that are taking the engineering 120 and 220 series. And so I'll try to talk you through the steps involved. So trying to find a couple of old problems here real quick. sure, 18, I think. Sorry, my other computer's being a little slower than I had anticipated. All right, so what I would like you to do is, sorry, express this polar form, or excuse me, rectangular form complex number A is equal to negative 18.5 minus J 26.1 as a polar form complex number. So what my expectation is that you'll give it to me in the form A. Actually, let's not do polar form. Let's do, polar form, sorry. A angle theta A. Now, we can do this by hand, actually pretty trivially, but we might find out that if we do it by hand, we're going to get a different number than what we would get if we used our calculator to just explicitly do the math. So for those of you that are using a TI calculator, how you would do this is you would press the, this is going to be annoying as shit, just to give you a heads up. Obviously, you press the negative key, then the 1 key, then the 8 key, then the period key, then the 5 key to do negative 18.5. I know I probably didn't have to explain that to anyone, but just for the sake of argument. Then you would press the minus key, then the 2 key, then the 6 key, then the period key, then the 1 key, and then you would press the key that has pi and then E and then I, and you would press that guy 3 times. And then press enter. So somebody with a TI calculator, tell me what your calculator does when you type in that series of key presses.
Get negative 18.5 minus 26.1i.
Okay, so it's giving you your answer in a rectangular form complex number. Okay, so you typed in a number and it spit out effectively exactly what you put in. We can make our calculator give us the answer as a polar form complex number in one of 2 ways. And it really kind of just depends on your preference. And so what I mean by that is we can go into the mode section of our calculator. So we press the mode key, and down at the very bottom, it should say real, then A plus BI, and then R angle theta. So if we were to move our cursor over to where it says R angle theta, that is us telling our calculator that our preferred format for complex numbers is polar form. So we could make it effectively always give us our answer in polar form. That's one way to do it. The second way would be to press, I'll do this in a different color. Press the second button, then that pi EI button, and then press the 4 button. And what that's going to do is convert our answer to polar form. So once we convert our answer to polar form, what did we get? Anybody?
$31.99 and some other numbers behind that. Angle negative 125.329 and some other numbers behind that.
So negative 125.329. So it is important here that we recognize that that is in degrees, because we could have, if our calculator was set in radians or in radian mode, that angle that is returned to us could be vastly different, obviously, because it would range somewhere between 0 and pi. All right. So for the TI folks, I'd like for you to just kind of play around with your calculator for another minute or so, just kind of entering in complex numbers, and make sure that you're familiar with how to convert from rectangular into polar. And you could also go potentially the other way around as well if you did that second pi key and then 5. So now Casio folks. The first thing that you need to do, turning your calculator on, and this is going to take me a little bit longer because I so infrequently use my Casio, is press the mode key. And then press the 2 key. That sets your calculator up to interpret complex numbers. So you have to do mode and then 2 before you do literally anything else. Then large, same thing. So I'm just going to try to copy some of this. Obviously, the negative 18.5 minus 26.1 part is literally going to be exactly the same. But for you to enter in the imaginary operator, you don't have to press any buttons 3 times or anything like that at all. You just press the engineering key, ENG. So if you don't mind, somebody do that series of key presses and then tell me what your screen says.
I got negative 37/2 minus 261/10I.
Okay, so it's giving, so negative 37/2 is the same as negative 18.5. And obviously 261/10 is just 26.1. So you could get it, like if you press that S arrow D key to get it from fractions into decimals, you would be getting the number in, your complex number in
Oh,
polar
yeah.
form as well,
Yeah, I see that.
exactly as we entered it in. So your question may be how to change that. All right. So you also, Casio users also have two options. You can either choose that your answer is always given to you in polar form, which is accomplished by pressing Shift and then the mode key. That'll bring up a menu with 8 different options. If you press down, option 3 is your settings for complex numbers. And then it asks you whether you want your results to be expressed in rectangular form, which you would press number 1, or polar form, where you would press number 2. So to be clear, what I did at that part, Shift, mode, down, 3, and then 2. So this is all answers will be in polar. If you only want this particular answer in polar, instead, you would press Shift, two, and then you would press the 3 key, which will convert your current answer into polar. So using either of those options, please tell me what answer you get.
I got 31.99, and then I think it was in the negative 125.32.
All right, so you got this number effectively.
Yeah.
All right, so without me walking you guys through it, I would like for you to do this guy. And tell me what the answer should be in polar form, please.
I got 37.94 for the magnitude, 37.95, sorry, and 124.7 degrees.
Perfect. All right. So that is how you use your calculator to convert an answer to polar form, okay, or convert a rectangular form complex number into polar form. Now, if we did, let's see, that would be, all right, let's do this C by hand and see what happens, okay? So by hand, the magnitude of C would be the square root of negative 21.6 squared plus 31.2 squared, which would give me see, gotta remember where the square root key is on this calculator. 21.6 squared plus 31.2 squared, 12 square root of 10, or 37.947. So that part matches up pretty well. The angle would be the inverse tangent of 31.2 divided by negative 21.6.
Negative 55.3.
All right. Yeah. Negative 55.3 degrees. Which is not the result that we got by using the calculator's internal way of doing it. Does anybody know why? Or does anybody know what, let's start with maybe a little bit easier question. What's
Would
the
it be
difference in those angles?
would it
It's
be measured
going-
just off the positive x-axis?
Yeah.
I do 180 minus that, or
Yeah, so effectively the issue here, our answer is 180 degrees away from what it needs to be. And the reason is that our calculator can't tell the difference. So it interprets tangent, inverse tangent of 31.2 over negative 21.6 to be identical to the inverse tangent of negative 31.2 over positive 21.6, which seems fairly reasonable, right? So effectively, our calculator doesn't know that our complex number is supposed to be in the second quadrant, which we can easily see by looking at the rectangular form, okay? So this is why I literally prefer you guys to learn how to do this math on your calculator as opposed to doing it by hand, because by hand introduces these small errors if we're not paying very, very close attention to what's going on, right? So in the complex plane, just to be clear here, here's our imaginary part, here's our real part, and I'm just gonna kind of half-ass draw this guy. In rectangular form, we go out negative 21.6, and then we go up 31.2. And so this should be C. And it's obvious then that we should have an angle that is positive and greater than 90 degrees. When we did it by hand, we wound up with effectively this guy, which has an angle of theta C minus 180 degrees, right? So it's going to have the right magnitude always, but the angle of any rectangular form complex number that is in quadrant 2 or quadrant 3 will always give us the wrong angle by exactly 180 degrees. So legitimately, doing the work by hand is much worse for you guys than plugging and chugging using your calculator. Have I illustrated that point enough?
Yes.
All right. So now let's go the other way around and let's figure out how we're going to input numbers in polar form, okay? So let's say that I have the number A is 36.2 angle 108 degrees. So TI folks, I'm not going to go through the button presses of 36.2 this time, but how I get that angle key is I press second, then the pi EI key, and then the number 1. So I could do 36.2, second pi 1, that gives me the angle sign, then 108. For the Casio folks, the angle key comes from hitting shift and then the negative sign key. To convert our polar answer to rectangular for the TI folks, so to convert our answer to A plus BI involves pressing second pi EI and then 5, if I'm not mistaken. Or you could go back into your settings and just make it always give you the answer in rectangular. And for our Casio friends, converting to rectangular involves hitting shift 2 and then 4. So somebody, preferably somebody who hasn't spoken up in a bit, please tell me what the rectangular form representation of this complex number A should be.
I got a minus 11.186 plus 34.428.
I'm sorry, I couldn't really hear you that well.
Yeah, I got a minus 11.186 plus
Negative.
34.428.
34.428, which is exactly what I got. Did everyone else get the same thing?
Yes.
All right. So there's another potential pitfall here. I could give you, let's say I gave you the complex number B is equal to negative 19 angle 15 degrees. I'd like for you guys to try to tell me what that answer is in polar form, and let me know how quickly you get a math error.
Immediately. That's how quickly I got a math error on my Casio.
Yeah, so for all of the Casio people, you're going to get a math error, and for all of the TI people, you're not. So how we rectify this is literally just say negative open parentheses 19 angle 15 degrees, and that should solve it. And what you'll find is that you'll get 19 with an angle of negative 165 degrees. Okay, so the TI people, the calculator can interpret it. For whatever reason, the Casios, it can't. But if you put parentheses around the complex number, that it interprets just fine. It interprets it just fine. So I'd like to take a moment here to explain what's going on, actually. Not necessarily what's going on with your calculator, but it's interesting as how the number -1 is interpreted, okay? So we take our complex plane, here is our real part, here is our imaginary part, and let's say that I go out 1 unit in the real direction. As a rectangular number, this is simply 1 plus J0. And as a polar number, this is 1 angle 0 degrees. If I go 1 unit up in the imaginary direction, this is J, or 0 plus J1 in rectangular form, or 1 angle 90 degrees in polar form. If I go 1 unit in the negative real direction, that's -1 as we are accustomed to seeing it, or it's -1 plus J0 in rectangular form, or it's 1 angle 180 degrees. And I can write plus or minus 180 degrees here because it doesn't matter whether it's positive 180 or negative 180. So later on in this class, you'll see me use plus and minus 180 degrees, just kind of depending on what my current mood is. They represent the exact same number, so it's unimportant. And then if I go 1 unit down in the imaginary direction, I have negative J, which is 0 minus J1, or 1 angle minus 90 degrees. So the math that I'm implicitly doing here is actually 1 angle negative 180 degrees multiplied by 19 angle 15 degrees, or 1 times 19 with an angle of negative 180 degrees plus 15 degrees is what gives us 19 angle negative 165 degrees. So it's going to take a while to train your brain to think of a negative sign effectively as a complex number, but that is exactly what's happening when we do this math, okay? So it will be rare that we will ever see complex numbers with negative magnitudes, but we will pretty regularly subtract complex numbers. And for those of you with a Casio calculator, if you forget to put in those parentheses, you're going to wind up getting a math error every single time. So I just wanted to point that out. All right. So now let's say I have a complex number A that is 5 plus J8. And what I want is a conjugate in polar form, right? So this would be A with an angle of negative theta A. Now, you could, now that you know what a conjugate is, simply type in 5 minus J8 into your calculator and convert that answer into polar form, and there'd be nothing remotely wrong with that. But our calculators can actually do the conjugate operation for us, okay? So for those of you with a TI calculator, the conjugate operation is accessed by pressing second then that pi EI button, which that's how you access the complex menu. And then if you scroll down to number 6, that's the conjugate operation. So if you press 6, it'll say CONJ, open parentheses, and then you could type in your complex number and it'll spit out the conjugate of it. And then you get to choose whether that answer is in rectangular or polar format. For the Casio users, accessing it is similar. It's Shift 2. Shift 2, and then 2 again. That brings you to the conjugate. And then for you guys, it'll be capital C ONJG, open parentheses, and then you input your complex number. So somebody please tell me what the polar form of the complex conjugate of complex number A is.
Would you happen to know how to do that on, like I have a Casio, but it's the 991. Like, would you happen to know how to do that?
I don't remember off the top of my head because I don't have the keypad in front of me. Let me look it up real quick on the internet. Casio 991 complex conjugate. So I believe when you're in complex mode, press the option button to access your complex menu.
Yeah, I see it now.
And then number 1 returns the argument. So actually, I can talk a little bit about what all this crap in. So now that we all know, or hopefully all of us know, how to access the complex menu in our calculator. So for TI users, it's literally just pressing the second and then the pi button. For Casio users, you put your calculator into complex mode, and then if you have the FX115, you press Shift 2. If you have the 991, you press the option button, and you should see stuff on there that says like ARG. That stands for argument, and what the argument function does is returns the phase angle only. Then the conjugate operation obviously gives you performs the conjugate, so it either changes the sign on the imaginary portion or changes the sign on the angle, depending on whether you're working with a polar form complex number or a rectangular form complex number. The real part just returns the real part of the rectangular form, and the imaginary for the Casio folks, or for the Casio 115 folks, I don't remember if there is a real and imaginary operator on your calculator, but I know for the 991 there is, and I know for the TI folks there is. But if you can get your answer explicitly in rectangular form, which you know how to do, it's pretty, you can just read it off. I'm trying to see. That doesn't do it. That doesn't do it. Sorry, I don't see anything obvious for separating the real and imaginary parts with the Casio FX 115. But again, if you can get the answer given to you in rectangular form, the part with the eye is the imaginary part and the part without the eye is the real part. So it's not particularly difficult. And for the most part, I'm not going to make you do operations on the components of a complex number. So I don't know that we ever actually circled back around to solving the question that I've asked you, which is what is the conjugate of that 5 plus J8 complex number expressed in polar form?
I got 9.43 for R or for A and negative 57.8 degrees for the angle.
I get negative 57.995. Yeah, degrees. Okay, so I believe that we are in reasonably good shape here. So now I would like for us to take care of a couple of problems that involve stringing together some mathematical statements, I guess, using our calculators, okay? So let's say that we have a complex number A, and it is -2 plus J6. We have a complex number B that is 4 plus J7, and we have a complex number C that is -6 minus J5. I want to know what A multiplied by B plus C is equal to, as one thing. And then I want to know what A conjugate times B times C is equal to. So how I would approach a problem like this personally is I would simply store those three complex numbers, A, B, and C, as variables in my calculator, and then just do the math using those variables. So does anybody not know how to store numbers in their calculator? Let's start there.
I'm not 100% sure.
All right, are you a TI person or a Casio person?
TI.
All right, so for TI, to me, TI is a bit more straightforward than Casio. So let's start with that -2 plus J6. So I would do -2 plus 6i. Once I get that on my screen, I press the store button. And then I press that button directly above store, which has X, Y, Z, T, A, B, C, D on it. And I'm going to press that button 5 times to bring up the number A, or the letter A. And so that literally stores -2 plus 6i as variable A. And I would repeat that process for B and for C, storing them as different numbers, or different letters, excuse me.
Okay, I kept getting a syntax error because I thought you had to use letters over the number buttons, so that doesn't work.
Yeah, I don't even know what those letters over the number buttons are for. Maybe it's actually, maybe there's a way to set the calculator in hexadecimal mode, because that would make sense given that you only have access to A, B, C, D, E, and F.
Actually, I think you can.
But the variables are all accessed by pressing that X, Y, Z, T, A, B, C, D button. Or at least I've never needed more than 8 variables, so I always just use that button. For the Casio folks, I think it's pretty similar. So let me type in -2 plus 6i. Then you hit Shift, recall, and then to access variable a, you would press the minus sign. And so that's, your screen should go blank for a second, and then it'll look like -2 plus 6i, arrow, capital A, and then it'll also spit out the answer to that in either your preferred format of rectangular or polar. Repeat that for obviously complex number B and complex number C. And then doing the math becomes fairly trivial. So let me store the other two. 4 plus 7i stored as B. Shift, recall. There we go. And then -6 minus 5i, shift, recall, C. And so for part A, now that I have all my variables stored, I literally just hit alpha on a Casio, alpha A multiplied by alpha B plus alpha C. And I get an answer. And on the TI, I just hit that X, Y, Z, T, A, B, C, D button until I get A, open parentheses, hit it again a bunch until I get B, plus hit it a bunch again until I get C, close parentheses. So please tell me when you have an opportunity what you get for A multiplied by B plus C.
You want it in rectangular or polar?
Take your pick.
In rectangular, I got -8 minus 16j.
Yep, -8 minus J16. And for those of you doing it in polar form, that is 17.888. Angle -116.565 degrees. All right. So now figure out what the conjugate of A multiplied by B multiplied by C is.
I got -394 plus 58J.
Let me convert that to rectangular. So -394 plus J58. Yep. And converted that into polar form. That is 398.246 with an angle of 171.626 degrees. All right, so we've plenty of stuff today, and we're actually only 20 minutes out from the end of the class, so I'm going to be wrapping things up here. I will tell you, on your web work, it's going to be actually fairly similar to what we did in class today. There's just one question that typically messes with the students a little bit, and it's because some of your calculators don't know how to interpret this. And I think the TI-36s can't do it. The Casio FX115s can't do it, but the Casio FX991s can. So for those of you that don't have the Casio 991, like to talk to you about real quick. So on one of your homework problems, it has something about j to the 7th power. And so I'd like to just take a moment to explain how j behaves, all right? So if I have j to the 1st power, this is simply j, which is equal to the square root of -1 by definition. J to the 2nd power is then the square root of -1 squared, which is -1. J to the 3rd power is j to the 1st power times j squared. So that's going to be -j. J to the 4th power is j squared times j squared is +1. And then j to the 5th is j to the 4th times j to the 1 is just j again. And it cycles over and over and over again. So j to the 5th is the exact same thing as j to the 1. So effectively, if you ever have a power of j that is over 4, you just subtract 4 from its power to get the answer. Similarly, j to the 0 by definition must be 1 because anything to the 0th power is 1. J to the -1 is 1 over j, which is 1 over the square root of -1, which looks like -j. So just to prove that real quick, 1 over j multiplied by j over j gives us j over j squared, or j over -1 is -j. We could have also got that by looking at j to the 3rd power. If we subtract 4 from that, we get j to the -1, so they have to be equal. J to the -2 is 1 over j squared. So that's 1 over -1 is -1. J to the -3 is 1 over j times 1 over j squared. So that's going to be -j times -1 is +j, and so forth. So hopefully you all can see that it literally just cycles between these 4 values. It goes j -1, -j1, j -1, -j1 over and over and over again. So if you can remember, these 4, then you literally know how j to any power behaves. If it's outside of that range, you either add enough 4s to get it into that range, or subtract enough 4s from the power to get it into that range, and then you know how it behaves. So again, on the homework problem, it's got something like j to the 7th c plus b is really the same as j to the 3 c plus b, which is just -j times c plus b. So anyhow, so that's enough out of me, I think, for today. If anybody has any questions, I would be happy to stick around and answer them. And if not, I will see you guys tomorrow, where we will talk about sinusoids for a long freaking time.
I do have a question about the equation sheet on the exam.
Yes, sir.
What is fair game to put on it, and what would you like say, oh, you can't put that on there?
Anything that you can write by hand and read without the use of an external device is fair game to me. It does not bother me whatsoever if you put equations on there or worked out practice problems or whatever.
Yeah, I was wondering because I'd put like I'd wrote out my equation sheet and I was like in a DC steady state, like this is open, this is a short circuit, stuff like that. And I just want to make sure you didn't want just equations on there.
Nope.
Okay.
No, I had a student, this was in circuits too, several years ago. I allow them to use equation sheets on every test. And his equation sheet was full of nothing but the dumb shit that I had said in class when I was wrong. And I let him use that. So, I mean, I don't, as long as you write the equation sheet so that it's not a photocopy of someone else's work, I don't have any issue with you putting what you either put or don't put on it.
All right. Thank you, sir.
Mhm. As long as it's just one sheet.
Front and back, or just the front? Just curious.
I'm going to say front and back. Typically, honestly, I would prefer just front, but because I don't know that I'm going to have, well, I'll have this video up tonight, but I don't know how many students are going to watch it all the way to the end to see that there's questions being asked about the exam. So because I didn't make it clear on my emails that I really think that you guys are probably tired of me emailing you about this test, I'll let this one be front and back without any issue.
All right.
I mean, to be honest, you need 4 equations and you're finished, in my opinion. Well, like if to me, if you wrote down the equations for the current voltage relationship for an inductor, so those 2 equations, the power relationship for an inductor and the energy relationship for an inductor, and then understand the concept of electrical duals, you have all the equations that you need for this test. But you guys may disagree because you're not jackasses with PhDs like I am. All right, anybody got anything else? Okay, I will see you all tomorrow at 10.